Hi everyone, I'm Satya and I'm here to talk about sound and complete proof rules for probabilistic termination. This is joint work with my advisor Rupak, and we're both affiliated with the Max Planck Institute for Software Systems. Right? And before I get into the meat of our work, let me start with the mention of our program model. Well, we include the basic imperative programming constructs like while loops, if conditions, and so on, and we allow our program variables to take on rational numbers. In addition, we allow for finitely branching probabilistic and non-deterministic choice. This means we can have single instructions where you can increment or decrement a program variable x with equal probability, or you can non-deterministically either increment x, decrement x, or increment y. All right? However, we do not allow for random sampling or for unbounded non-deterministic branching. This means we cannot uniformly sample a number between 0 and 1 and assign it to a program variable x. Similarly, we cannot non-deterministically assign any natural number to a program variable x either. All right? So in this model, we're interested in the termination question. And what is termination in a probabilistic sense? Well, we studied two notions of termination. The first is what we call the qualitative notion of termination, where we ask whether the probability with which a program terminates is 1. And the second notion is the quantitative notion, where we ask for proofs of lower bounds and upper bounds on the probability of termination. Now, note the asterisks over there. That's because of nondeterminism. Because we resolve nondeterminism demonically, the probability of termination of a program is interpreted to be the smallest possible probability across all possible resolutions of nondeterminism. All right? So our program model is obviously Turing complete, meaning that these questions are undecidable. And the way we plan on answering these questions is to use proof rules for termination. And what are these proof rules? Well, proof rules are simply a collection of formal conditions written in a formal program logic that, if met by an input program, implies its termination. How they work is that they kind of encode the certificates of the program's termination as conditions in a formal program logic. The classical example of a proof rule for termination would be the ranking functions. These are just functions that decrease by at least 1 at each execution step. You can kind of see that in this particular very simple while loop over here, the simple function that outputs x is a ranking function. All right? To properly capture probabilistic termination, we want these proof rules to be both sound and complete. Soundness means that if we find certificates matching the proof rule for a particular input program, that means that that program definitely does terminate, right? And completeness means that if you have a program that definitely terminates, then there will exist some certificates that match the proof rule for the program, right? So we want both soundness and completeness. And for non-probabilistic programs, the ranking functions that I mentioned earlier are already sound and complete for termination. Unfortunately, for probabilistic programs, the current state of literature is that we don't really have completeness. For qualitative termination, the closest thing we have is completeness in this case of finite state programs. This is work by Annabel McIver and Carol Morgan in 2005. And in fact, the closest thing we have, the state of the art, by Annabel McIver and a few others at POPL 2018, was believed to be incomplete, even by the authors of that rule itself, right? Even though there are no counterexamples, they still believe the rule was incomplete. Things aren't great for quantitative termination either. For the case of lower bounds, we had a proposed proof rule by Chatterjee and a few others in 2022. This rule was proposed and proved to be complete, but unfortunately, this completeness proof has a small bug. We have shown a small counterexample to their completeness in our paper. So at the end of it all, we don't really have a complete proof rule for probabilistic termination, and our contributions is to give that. we show the first sound and relatively complete proof rules for probabilistic termination. Now, I've been talking about soundness and completeness. Well, what is relative completeness? Well, in addition to completeness, we also show that for all terminating programs, there will exist certificates of termination that can be encoded in the program logic, meaning that they can be expressed in the program logic as well. All right? This is important. This is necessary to fully reduce the problem of termination to a problem of program logic validity. Right? Now, again, there's an asterisk over here. That's because we've shown, honestly, to even our surprise, that the prior state-of-the-art rule was also complete. Okay. So I don't have a lot of time in this talk, so I'm going to focus in the rest of the talk on qualitative termination. All right? I will derive our proof rule for qualitative termination, which was also called almost sure termination. That's what AST stands for. And I will derive our proof rule for qualitative termination by analyzing these three example programs. The first is a simple coin flipper. It repeatedly flips a coin until the coin lands tails. The second and third are random walkers that navigate the integer number line. The middle one is unbiased. The last one is biased away from the origin. Both these random walkers stop when they hit the origin. All right? And how I will derive our proof rule is, well, I'll start with an earlier proof rule, and I'll try to kind of fix it so that it can actually apply for all three of these programs. All right? And what is this earlier proof rule? Well, this is the proof rule by Annabel McIver and Carol Morgan that I mentioned earlier that was, well, complete for finite state systems. Right? This is called the variant rule, and it generalizes the ranking functions that I talked about earlier as well. How does that work? Well, you take the ranking functions, they must decrease at each execution step. The variant functions must also decrease at each execution step with a minimum probability amount. And because it must decrease at each execution step with just a minimum probability, there is a probability with which it can increase. So let's just bound the variant rule to make it sound. All right? Let me be a bit more precise. In addition to finding the function itself, u, you also have to find an epsilon so that u will decrease with probability at least epsilon at each execution step. This is the variant rule, and you can see its operation in the coin flipper. As long as you have just the function u that is 1 when the coin lands heads and 0 when the coin lands tails, this function will decrease by 1 with probability at least half at each step. All right, and this function over here certifies the termination of the coin flipper. Now, the variant rule is unfortunately incomplete. And this is something that is witnessed by the symmetric one-dimensional random walker, which is almost surely terminating, but cannot be shown so by just using the variant rule. And this is because you can kind of see that the candidate variant rule, if you were to try to build a variant for this, you would notice that the candidate variant rule that you would build, which just outputs the value of x at the program state, is unbounded. And this is just because, well, the integer number line is unbounded. It will reduce with probability at least half at each step, but it is unbounded, so we can't use the variant rule here. But can we get away with this? Can we get away with an unbounded variant? Well, no, because unbounded variants are unsound. And this is, again, witnessed by the asymmetric random walker, for which this unbounded variant would actually imply AST, because it would still reduce, but with probability at least 1/3 at each execution step. All right, so what do we have? We have a variant rule. That's pretty nice. It generalizes an earlier rule that we used to use for non-probabilistic systems, but it seems to be unbounded for certain programs. And the difference seems to lie somewhere between the asymmetric and symmetric random walker. All right, so let's go a little deeper into this difference. This is just a symmetric random walker in a more picturesque way. And let's be a bit creative. Let's put a wall to the right of the random walker. And how the wall works is that when the walker hits the wall, he stops moving, he stops walking. So, yeah. In this case, if you remember the earlier candidate variant that we had, it's now bounded by the wall, by the position of the wall. Therefore, this walled-off random walker is definitely terminating. This is not incredibly surprising news, but this is something that we do have. But a cooler thing is that the probability with which you hit the wall grows smaller the further away the wall is. In fact, for any possible epsilon, there is a position for the wall so that the probability with which you actually reach the wall is less than epsilon. This is a very nice observation, and the even cooler part is that this is not true for the asymmetric random walker. We have seemed to have found a property that holds for a symmetric terminating random walker, but not for the asymmetric one. This is very nice. But this is not even the coolest part. The even cooler part is that this generalizes for all terminating programs. It turns out that you can take a terminating program, order its states. And if you manage to do this, you can always show that the probability of reaching states far to the right of where you currently are is very small. So from here, if you start from the state in the middle, which is like indexed n, there will exist an m. For an epsilon, there will exist an m, so that the probability of reaching states indexed m, m plus 1, m plus 2, and so on, is less than epsilon. And because of this, because this is an indexing, and the rest of the states must be indexed values less than m, meaning there are finitely many of them, meaning that any variant that you could possibly create for them will automatically just be bounded. All right? And this is something that is true, and this observation is something that we use heavily in our completeness proof. All right? How do we use this observation, though? Well, we use supermartingales to witness this observation. And these are simply functions that, in expectation, do not increase at each execution step. All right? For the symmetric random walker, the simple function that just outputs x at each execution, at each state, is a supermartingale, because in expectation, the next step, you are going to increase x with probability half and decrease x with the same probability. So in expectation, you don't actually change the value of v after a step. So this is a supermartingale. All right? And how do supermartingales work? Well, it turns out that the probability with which a program's execution increases a supermartingale from a low value L to a high value H is bounded above by L by H under certain conditions that we actually incorporate into a proof rule. All right? To make it a bit clearer, in the case of the walled-off random walker, the supermartingale kind of shows that the probability with which you reach the wall is less than n by m, meaning that for an epsilon, all you have to do is find a value of m so that n by m is less than epsilon. And since m is not bounded, we can definitely always do that. Now, we have not really used the supermartingale to show termination. We've only been using the variance to show termination, right? The cool part here is that the variant is bounded when the supermartingale is bounded. If you have a collection of states within which a supermartingale is bounded, the variant will also be bounded. And it is possible to show that because of all the observations we've seen so far, you cannot really come up with a supermartingale and a variant such that this particular property will hold for the asymmetric random walker. Okay? So let's summarize. What do we know? We know that with the bounded variant, we have almost sure termination. We know that with unbounded variants, we don't really have anything. But if we have a unbounded variant that is bounded when an associated supermartingale is bounded, we seem to have almost sure termination. And this third point is exactly our proof rule for almost sure termination. We want a variant, which is both of these, and a supermartingale, which is this, such that both the variant and the supermartingale are 0 only at terminal states. These 2 points just mean, this point just means V is a supermartingale, this means U is a variant, such that when the supermartingale is bounded, if it's bounded by a real number R, then the variant must be bounded by some number HR, right? In a collection of states where the supermartingale is bounded, the variant will also be bounded. Now, for a technical reason, we can kind of move this epsilon a bit down, and we'll get a sound and complete proof rule for almost sure termination. All right? And to summarize our work, in our paper, we have shown a new sound and complete proof rule for almost sure termination, and we've shown that the earlier state-of-the-art proof rule by Annabel McIver and a few of others is also complete using our completeness arguments. We also have a couple of sound and complete proof rules for quantitative termination that also use supermartingales and variants. And for future work, we're going to try to include random sampling in the program model and still see if we can maintain completeness. All right? Thank you for listening. I'm happy to take questions.
Great, so we have time for 2 questions. Right here.
Can you say something about the expected running time?
Not with these proof rules. I mean, for the expected running time, there do exist existing sound and complete proof rules for them. I think they just use what is called a ranking supermartingale, which is just a supermartingale that in expectation reduces by a minimum amount in each step.
Okay, thanks.
Couple. Let's go to the right there, right in front.
Great talk. I was wondering, the rule from the previous paper that you showed is complete. Can you tell us what differences there are? Is it stronger assumptions than yours?
It's actually quite interesting. So in our paper, we have a supermartingale and a variant, right? Over there in their paper, they have a function that is both a supermartingale and a variant at the same time. So it is a supermartingale that, in addition, must decrease by a minimum amount at each step. And as you keep going down, you have to keep decreasing by like larger and larger amounts.
Thanks for the talk. So you say you don't support sampling, but I mean, with just the choice operator and while loops, you can already
You can approximate it, but you don't. Yeah, but you can approximate sampling to an arbitrary precision, but I don't know if you can actually.
Yeah, I don't know if you can do anything, but you can certainly encode some discrete distributions, like geometric distributions.
Of course.
So do you have any intuition of what the challenges would be to actually have a sampling? Well, also, were you talking about discrete sampling only, and then if
no, I mean continuous sampling.
Okay, so then,
I want all kind of.
Okay, so then of course there's challenges.
It's just maybe let's talk about this offline. I mean, there is I can talk about this for a long time.
Sure.
Okay, great. We maybe have time for one more quick question if we do. If not, no.
Your probability must be a constant, or I can have 1 over x in this example?
You can have 1 over x. It's okay. Not sure it'll be complete though. I mean, terminating though.
All right, great. Well, that wraps up the end of our session. Let's thank our final speaker.